All right, good morning, folks. I'm going to go ahead and work through these 4 problems from your joke worksheet that should have been given to you. Please notice that there are 4 problems at the top. There are also 4 diagrams that go with them. At the bottom, each question has 3 parts that you're going to use for the joke. So part A is basically telling me what you know and what you're trying to find. Part B is the static equation that you're going to find. And then part C is from that same choice of those middle boxes you see there. That would be then what you get when you derive the static equation. And then part D, so excuse me, there are 4 parts to each question. Part D then is actually finding the answer. So let's go ahead and take a look at number 1. I have water flowing out of a cylindrical tank. Okay, so right there, I have a cylinder. I have water in it. That is probably going to be the volume of a cylinder formula, which is that. Okay, so that's the static equation that I'm going to use. Okay, now you'll notice that that is not one of your choices down there in that middle section, because I also need to figure out what I know and see if I can plug anything in here. Let's see here. I have flowing out of a vertical cylindrical tank a radius of 2 meters. So my R is 2. At a rate of 4 meters per second cube. So that is dV dt. Okay, the volume is changing and it's going out. So that is going to be -4. Okay, it says find the rate at which the water level is changing. So that would be the height. dH dt is what I'm trying to find at any moment in time. So this is what I'm looking at right now. Okay, this information over here matches up with letter, it looks like A, from those choices of given information. Now, with this cylinder, does the radius of my cylinder ever change? And the answer is no. So that means I can go ahead and plug in my radius to my static equation. So now I have V equals pi, we'll call this 4 pi H. And that is going to be my static equation from that middle section, which is letter A. Okay. Now I'm going to need to go ahead and derive this. So I have dV dt equals. Now, the derivative of this is just a linear term. There's no power on it but a 1. So when you derive that, you will get 4 pi, and then you need your dH dt on that. And now we're ready to plug everything in. Now, this equation that we just got corresponds with letter T from your middle section. Okay, so I guess maybe I should label these a little bit. This would be answer 1A. This would be answer 1B. And this would be answer 1C. All right, now we're ready to plug everything in and actually find it. So dV dt was decreasing by 4. So that's -4. And I'm trying to find dH dt. So go ahead and solve that. Move the 4 pi over, and you should get -1 over pi for dH dt. Okay, and my units on this should be meters per second. So that's my final answer, and that corresponds to letter A. So that would be your answer for 1D. Okay, moving on. Number 2, I have sand being poured at a rate, excuse me. Well, sand being poured, you can see the shape there, that's a cone, and this would be the volume of a cone. And the formula for volume of a cone we have used looks like this. Okay, so let's go ahead and take a look. Sand is being poured at a rate of 2 meters onto a conical pile of sand. So I am pouring sand at a rate of 2 meters cubed per second. That is dV dt, and that is 2. That's this number right here. Initially, it is 2 meters in height. Okay, so my height is 2. That's at the start. Okay, so let's just note that. With a base diameter of 6 meters. So the base is 6, again, at the start. Now, I want you to think about what's going to happen if I keep pouring sand onto this cone. Okay, it's going to form a new cone, and a new cone, and a new cone, and a new cone, depending on how much sand I pour on it. Okay, and those cones will all be proportional to the original cone. And you see here that they have already worked out this whole proportion thing that we did in that water problem we did at the end of class. Okay, so they've already made the proportion R over H. I think we did H over R when we did ours, but it really doesn't matter. And then they solved for the R, because this is the part that never changes. This ratio has to be the same. So that's something that we're going to be able to plug in before we take the derivative. Okay, but I do have one other piece of information. It says, how fast is the height of the pile increasing? So I'm trying to find dH dt, that's my unknown, when the pile of sand is 4 meters high. That would be the new one, I guess. Okay, so we're going to go ahead and plug in our R is 3 over 2H. Looks like that. And now I have V equals, let's see, that'll be 9 over 4, which will be 9 over 6. Okay. Let's see here. So, hold on a second. This will be 9 over 4 once I square it. And then if I multiply, that'll be 9 over 12, which will reduce to 3 over 4 pi h to the third. So that is my static equation, which corresponds to letter H. All of this information given over here corresponds to letter T. Okay, so this is answer 2A. This is answer 2B. And now I'm ready to derive this. So I get dV dt is equal to, that'll be 9 over 4 pi h squared dH dt. And now we'll go ahead and plug everything in. dV dt was 2. 9 over 4 pi, my h is going to be 2, and I'm trying to find dH dt. So go ahead and solve that. Okay, and when you do that, again, I suggest you pause and kind of go back and look and wait and make sure you got everything right. You should have 1 over 18 pi, and that is meters per second for dH dt. So this corresponds to letter E, which would be answer 2D, and we forgot about answer 2C, which would be this part right here, I think, which is letter L. Okay, so again, answering the joke is not what I'm getting after here. I hope that you're understanding the process as we go. Okay, next one we have another, a ladder problem. This is very similar to what we did in class. A ladder 5 meters long leans against a vertical wall. The foot of the ladder is being pulled away, that way, from the wall at a rate of 1 meter per second. So that would be dx dt is 1. Find the rate at which the top of the ladder is moving along the wall, so that way, which would be dy dt, at the instant when the bottom of the ladder is 3 meters away from the wall. So that would be x is 3. Again, it says note that we are sliding downward. So all of this information that we are given corresponds to letter E. Now we are going to use a Pythagorean theorem for our static equation. Please note that the ladder is not changing, so we're going to go ahead and plug in that 5 before we derive it. Okay, so this is your static equation, which is letter E of your choices. Now we're going to go ahead and derive this thing, which would be 2x dx dt plus 2y dy dt equals 0. Okay, and for this, they just kind of simplified it a little bit for your choices. Notice you can divide the whole thing by 2, so I don't need that. And then we're going to be solving for dy dt, so I'm going to move the x over. So we have y dy dt equals negative x dx dt, and that corresponds with letter R. Okay, so now we're ready to plug in. The problem is that I don't know what y is, okay, but I can use a Pythagorean theorem, which is 3 squared plus y squared is equal to 5 squared. Now, this is a 3, 4, 5 triangle, so my y is going to be 4. So it should look something like that. And when you solve for dy dt, you get negative 3/4 or negative 0.75. And your units on this is going to be meters per second. Okay, so that would be your final answer, which corresponds to letter T on your worksheet. All right. Last but not least, kind of a new problem for us, and we will be doing more of these. It says 2 cars are traveling along perpendicular roads, which you can see down here at the bottom, at 40 kilometers per hour and at 20 kilometers per hour. So car A is moving this way at 20 kilometers per hour. Excuse me, at 40 kilometers per hour. So that would be dx dt is going to be 40. Okay. The other car, car B, is moving at 20 kilometers per hour. So dy dt is going to be 20. Okay. It says when car A reaches the intersection, car B is 100 kilometers north and moving towards the intersection. Find the rate at which the cars are separating from one another. Now, if they're separating from one another, that would be this part right here. Okay, and notice they've labeled that as D. If that's what I'm trying to find, that will be dd over dt, which is what I'm trying to find. Okay, I also know, well, they also tell me that this is happening 2 hours later. So my time is 2. Okay. What else do they tell me? Let's see here. So car A is approaching this intersection. So when car A is here, car B was 100 kilometers away. Okay. So we know that as well. All right, so we need to go ahead and figure out a lot of stuff here. First of all, what equation are we going to use? We are going to use a Pythagorean theorem triangle, okay? We know that is, in our case, x squared plus y squared equals d squared, okay? But you'll notice that instead of y, notice that we are going to be subtracting the distance from 100, because I know it starts at 100. This guy is starting 100 away, and then it's going to keep getting closer. Okay, so that would be 100 minus y. So when I'm actually looking at my equation, I can make that substitution to look like that. And this will be letter D in your answer choices. Okay. All right, so now that I have this, what do I know? Okay. Let's see. I know that we're doing this for 2 hours. Okay, so if this is happening for 2 hours and I'm moving in the x direction right here at 40 miles an hour, okay, or kilometers an hour, excuse me. 40 times 2 means my x is going to be 80, okay? And then 20 times 2 right here means that my y is going to be 40. And then you can use your Pythagorean theorem to figure out that d is going to need to be 100. And again, I would suggest that you verify that. And again, these numbers that are in blue down there cannot be plugged in, okay, because they are going to be changing. It's not part of the static equation. Notice that we had to use this time in order to calculate those numbers. Okay, so let's go ahead and derive this. I will get 2x dx dt plus, now this is going to require a chain rule, so I suggest you break it up into your big and your small, but when you're done, you should have 2 times 100 minus y times -1, and then dy dt equals 2d dd dt. All right, I'm noticing they all have a 2, so I'm going to factor out a 2 and get rid of all those. And I now have x dx dt. Notice this is going to turn into a minus 100 minus y dy dt, and then d dd dt. Yikes, that's a lot of d's. Okay, this is letter S for your part C. These over here was also letter S for your 4A. I think I mislabeled that one back here. I think this should be 4B. Okay, so now that we have our derivative in front of us, let's start plugging stuff in. I know that x is 80, dx dt is 40, minus, now I have dy dt, which is 20, and then 100 minus y, well, the y is 40, so 100 minus y will be 60. And then I have equals, d is 100, and dd dt is what we're supposed to be finding. Okay, so you can go ahead and solve this. If we combine all the stuff together, we should get 2,000 equals 100 dd dt. If you solve for dd dt, you should get 20. And this is 20 kilometers per hour. Okay, and that is for dd dt, which is letter R on the joke. Okay, so hopefully that gives you a few more examples to take a look at, and hopefully you were able to kind of go through those. Please let me know if you have any questions on Friday, and we can talk about those. Otherwise, we will be doing more examples on these related rates and the implicit differentiation on Friday.